Continuing with our answer key for Gaussian and non-Gaussian calculations for electric field and potential. We start with a very long line of positive charge with uniform charge density. And we have a point P, with distance point P away from here, in the middle of that charge. So we do have symmetry. So we can use Gauss's law, and we'll draw a cylinder. Our integral is the closed surface integral of E dot dA is equal to Q inside over epsilon naught. Well, let's calculate Q inside. Well, since it's uniform charge density, lambda, of course, is Q over X. Therefore, Q equals lambda X. So that's what we're going to put in there. And of course, we're going to call a cylinder is going to be our Gaussian surface. We'll call a cylinder of length L. So that our Q is going to be lambda times L. And we're going to place that in for Q inside over epsilon naught. Now, we need the surface area of our cylinder, and that's just going to be equal to the 2 pi r, the circumference of this. Okay, r in this case is the distance P away from the center. And we're going to multiply that by L. So E dot 2 pi letter P times L equals lambda L over epsilon naught. Canceling out our L's, electric field is lambda over 2 pi times the letter P, which is our distance from the wire, times epsilon naught. Now, next case here, we have a line of positive charge, still with the uniform charge density, but our letter P is off to the right, so it's closer to this end. We do not now have symmetry. So we have to use a non-Gaussian way of doing this. Now, there are two unique directions here. There's one in the X and there's one in the Y. Well, let's take a look at what's going on here. So I've got a dq on this side. That, of course, is going to be pushing on a positive test charge this way. And here's our angle theta. And I've got a dq on this side. And, of course, it's going to be pushing on this side here. These are going to be asymmetrical pushes because this is asymmetrical. But let's take a look at our triangle. This is angle theta. So is this. This is the letter P. The hypotenuse, then, is the square root of x squared plus p squared. So the distance from dq to our point charge is always x squared plus p squared under a square root. And of course, dq is going to equal lambda dx this time, where dq is an infinitesimal amount here. Okay. Now our driving integral, of course, is going to be equal to dq over 4 pi epsilon naught r squared. Now r squared, of course, will be x squared plus p squared in this case. All right, let's continue. Okay. So right now, we want to find the equations. We're not actually going to solve for this. So we cannot use Gauss's law for this because there is no symmetry. So we need to write an expression to determine the electric field in the y direction for position P. Okay, so dE is then going to be lambda dx over 4 pi epsilon naught. Our r squared is x squared plus p squared. And we're going to multiply that by the sine of theta. Okay. Now if we go back to our triangle here, sine of theta is going to be opposite over the hypotenuse. So sine of theta is going to be p over the square root of x squared plus p squared. So dE in the y direction will be lambda p dx over 4 pi epsilon naught. When I put the p there and then the x squared plus p squared, that's going to be x squared plus p squared to the 3/2. Now continuing, when we want the x, we have lambda dx equals 4 pi epsilon naught x squared plus p squared. This time times the cosine of theta. Let's go back to our triangle. Cosine of theta is going to be x, okay, over the hypotenuse. And that's listed here, x over the hypotenuse. So when we multiply that in there, dEx is going to equal lambda x dx over 4 pi epsilon naught x squared plus p squared to the 3/2. Now all we're doing is writing the differential expressions for these. So we're not actually going to be solving those. And that's how we handle the difference between Gaussian and non-Gaussian. When there is symmetry, we can use Gauss's law, makes things a lot faster. When symmetry is not there, we must use our deriving integral, or driving differential expression, dE is equal to dq over 4 pi epsilon naught r squared.